Welcome to Life Cycle Talks, a series of talks presenting the research front to keep you up to date with the science and application of the life cycle perspective. Today's life cycle talk will focus on the environmental impact of emerging batteries. We will deepen our knowledge and understanding of how to assess their environmental performance using the life cycle assessment approach. My name is Yulia Liu, and I'm delighted to welcome our guest today, Shan Zhang, a PhD student from the Swedish University of Agricultural Science. A warm welcome to you, Shan. Before we get started, I'd like to share a few practical details. All life cycle talks will be published and made available on the Swedish Life Cycle Center's YouTube channel. Please note that the raise hand function will not be used for life cycle talks. However, you're welcome to submit your question in the Q&A function, and we will select some of them for the Q&A sessions after Shan's presentation. Back to you, Shan. I'm curious about what motivated you to begin exploring this area of research.
Thank you for the very nice introduction and for your question, Yulia. So during my master's in environmental systems analysis, I realized how important it is to identify, assess, and solve environmental problems with the system thinking approach to avoid shifting problems from one stage to another. So life cycle assessment provides a structured way to employ system thinking. With the fast-paced development of battery technology, I found it crucial and also exciting to analyze and understand the emerging batteries' environmental performance using life cycle assessment, which is why I choose to work on this topic.
Thank you. And now it's time for your life cycle talk.
So this talk will start with a short background and followed by the introduction of two types of LCA, small scale and prospective LCA. And after that, we will focus on prospective LCA. And the focus will be mainly on how to deal with the missing data. And so this talk will end up with a case study. So batteries have been a very essential part of our daily lives, powering everything from small devices like wearables, phones, laptops, to different types of electric vehicles, and large stationary energy storage. So current lithium-ion, these different applications require different requirements on batteries. And current lithium-ion batteries has its limitation to fulfill certain requirements in some market sector, which encourage the development of emerging batteries with higher specific energy, for example, solid-state battery, lithium-sulfur, lithium-ion batteries, or with low cost, such as sodium-ion batteries, or with innovative features like bendable or flexibility. So it's very important to consider their environmental performance at the early development stage, so the battery design can be modified to prevent the unintended environmental consequences. Life cycle assessment is a method that can be used to quantify the performance of a product, process, or an activity. So in terms of emerging batteries, the life cycle of it can be simplified as starting from raw material extraction, followed by material processing, transportation, precursor material production, battery manufacturing, to the final battery product. And energy is required for almost all the production processes along the life cycle, sourcing from a combination of fossil fuel and renewables. So given the low technology readiness level TRL of the current battery technology, of the emerging battery technologies, part of the so there's often only small scale data available for the foreground system including battery manufacturing processes and some precursor chemical production. For example, some cathode active materials in the sodium-ion batteries, or solid electrolyte in all solid-state batteries. And additionally, normally only small-scale data available for regarding the battery technology as well, like the battery composition and performance. So if we conduct a LCA based on the current system, the current emerging battery system like this, it is a small-scale LCA, usually called lab or pilot scale LCA. And the results can only be served for short-term decision-making with limited scope. So there's another type of LCA called prospective LCA, which focuses on the emerging battery technology at future point in time when they are produced at scale. So we know that our current society are undergo a rapid transition to a fossil-free economy. Many production processes along the life cycle will change in the future. For example, the transportation sector will be electrified, more materials will be recycled, efficiency of material and energy in some processes will increase. CO2 capture and storage technology might be implemented in some sectors. And the energy source will be greener. These changes are related to the background. As for the foreground, they will be upscaled to industrial level, as well as for the battery technology related data. It will be optimized to industrial scale, of course. So if we conduct LCA based on this, the future system, the future battery system, it is called prospective LCA. So the difference between prospective LCA and small-scale LCA lie in these three areas: background and foreground production processes and battery technology. In the following slides, we will look into the details how to consider the changes in these three sectors when conducting prospective LCA. Starting from background production processes, actually, some LCA study assumes that the emerging batteries that they study will be on the market in the super near future, which allows us using the current LCA database, like the background LCA database, without modification. And other LCA studies actually considers the changes using integrated assessment model, IEMs. IEM explore possible future changes in different sectors under the well-established scenario, shared social-economic pathways, and climate target scenarios. So a Python package called Premise, which developed by Homensaki and his colleagues, which can be used to implement the integrated IEM outcome to LCA. And it does this by using the outcome to modify the corresponding production processes and emissions in the current LCA database. And the outcome will be a set of prospective LCA databases under different selected years, under different scenarios. And then we can just use these PLCA databases for our LCA calculation. As for the battery technology related data, it is very challenging to find or to estimate the direct or to find direct data for emerging battery technologies. But battery studies usually report electrode performance related data like aerial capacity or mass loading, which can be served as the input parameter to calculate the material required for emerging battery component in each battery cell. And to do that, we need to understand how battery is manufactured. In short, Anode and cathode paste are coated on current collector, and then the battery cell is assembled by winding or stacking anode layer, separator, and cathode layer into shapes like cylindrical, prismatic, or pouch cell. So the first step in this is to decide on the battery cell design, like the battery shape, size, and internal design, single coated or double coated for the anode and cathode paste. So in this step, the commercial battery design or the dimensions can be used as references, and battery researchers' opinion is very important as well. And this allows us to estimate the internal volume of the battery cell in combination with the thickness of the winding or stacking layer. We can calculate the total surface area of each component, and specifically the thickness of the cathode of the electrolyte can be estimated based on the input parameters that we mentioned just now, and the thickness of the non-electrode like separator and current collector. This can be estimated based on the commercial battery cell. So using this surface area in combination with some physical material properties, we can calculate the required mass for each component, as well as the battery weight. And the next step, we can calculate the battery specific energy by multiplying the battery weight, battery capacity, and the battery voltage. So how do we calculate the battery capacity? For simplicity, we can assume it is identical as the cathode capacity, which can be calculated by the amount of the cathode active material with the cathode material specific capacity. So this serves as like a general framework that we can follow. For specific case, we probably some slight modification needs to be adjusted based on the available input data and also like the battery cell design. And this is like example study that you can read. So as for foreground system change, it includes battery manufacturing processes and the production processes of the novel chemicals. For the first part, a study conducted by Diggin and his colleagues estimated the energy consumption of different type of post-lithium-ion battery cells, which can serve as like a really good reference. As for estimating the material, the inventory for the future novel chemicals, simulation tools like Aspen can be used, but it's very time-consuming, also requires relevant skills. Alternatively, we can use some empirical factors and process equations in industrial process equations that is reported from previous studies to estimate the energy and material flows as well as emissions in each of the chemical steps for the novel chemicals used in emerging battery. For example, these thermal equations can be used to estimate the energy required in the chemical production process. So here comes to the case study. This is the results of the future climate change of 3 types of sodium-ion batteries and 2 types of lithium-ion batteries serves as benchmark under different studied years with 4 different types of scenarios, considering the background, foreground changes, as well as the changes in the future battery composition and performance. So the results shows that the climate impact increase over time, regardless of the scenario and battery chemistry. As for the environmental hotspots, different colors represent different material and energy flows, their relevant relative contributions to the total climate impact. We see that over time, it's the environmental hotspots also shifting. So in summary, this talk, we introduced like two types of LC that can be used for conducting emerging batteries. One focused on present time T0 with low TRL of the battery technology. It is lab or pilot scale LCA based on the system data that we have. Another one focused on the technology that the emerging batteries that is developed at scale in the future, TF, when their technology readiness level reached the highest. With upscaled foreground system and the future background system, as well as like the future battery technology related data. So this is prospective LCA. And when we conduct prospective LCA, we need to pay attention to the three areas, like is mentioned here. So these are some references that used in this talk. Thank you.
Thank you, Shan. And now it's time for the Q&A session. And I have a few questions for you. I will start with my own and then select some from the Q&A. Unfortunately, we won't have time to cover them all, but I will try my best to ask as many as possible. You introduced two types of LC. Who is the target audience for each?
Yeah, the target audience actually is different for these two types of LCA. For the small scale, because we focus on the current system with small scale system. So the scope of lab scale or pilot scale LCA, it's rather for the short term, not for the long term, which means that it's not really suitable for long-term decision making. So the target audience would be for battery researchers or chemical engineers, industrial process engineers, to help them to understand where's the environmental hotspots and to understand the environmental performance of current system better. But for prospective LCA, since we consider the system which is like, we place the system in the future, that's the future system. So that can also be served for longer term decision making for decision makers. Yeah.
Okay, thank you. And it seems like the lab scale LC has a limitation in terms of scope and target audience. And since prospective LC has a broader scope, then what are the limitations for prospective LCA?
So when we talk about future, it's always like there are much more uncertainties around. So I guess first is like there is like much more higher uncertainty around prospective LCA. And second, if we use, well, just now when we mentioned there are three areas that we need to consider when we conduct prospective LCA in batteries, right? One is related to the background system change. And one approach to consider that is to use IEMs. And we know that IEMs are actually focused specifically on climate change, climate impact change. So that's why we see a lot of prospective LCA, they only focus on climate, global warming potential or climate impacts, these categories, which sort of ignored other categories. I think that's one of the limitations, like the future prospective LCA database needs to be adjusted, also consider other impact categories as well.
Okay, thank you. Now we have questions from the Q&A. Regarding the prospective LC, what do you think is an efficient way of upscaling lab process to an industrial scale. Do you have an opinion on Piccinno's paper, which published on 2016?
Yeah, actually, that paper I think is a really good reference. And also it's very well used for scaling up, for quickly scaling up in prospective LCA. Yeah.
Yeah, the next question. Thank you for the interesting presentation. Why is the cathode the hot spot in the global warming potential? For example, because of high energy use or use of the certain materials?
That is mainly because of the production of nickel related and lithium, as well as cobalt related chemicals.
Okay, thank you. And we have the next question. Your focus is in lithium batteries, and that is relevant because they are the dominant technology. How about flow batteries? Can your methodology be applicable to them?
Yeah, it's also that when we conduct flow batteries, but we know that actually flow batteries, it has different working mechanisms compared to the battery that we talked in this talk. So if we use prospective LCA for flow batteries, for the battery design part, we have to adjust the method that is shared or the framework that is shared in this talk is not really applicable for flow batteries. That is a really good question.
Thank you. And we go to the next one. How confident can one be when calculating capacity based on cathode? Is it likely that the entire capacity gets translated to an actual capacity in the future finished battery product?
I'm not really a battery expert, so it's but from what I read, it's reasonable to use cathode active materials specific capacity to estimate the total battery capacity, and it's also quite commonly used in some studies.
Okay, thank you for that. Do you think any particular battery technologies have emerged as the most promising in the prospective LC studies?
Most promising in the LCA studies, so it's not in reality. So I think for sodium-ion batteries, that is quite good. In reality, sodium-ion batteries has its limitation regarding energy density, right? For serving the same amount of energy, it requires like a larger sodium-ion battery compared to the current lithium-ion batteries. But the climate impact but it doesn't really use like critical materials for sodium-ion batteries. Also, according to prospective LCA results, the current publications, its climate impacts are slightly lower compared to like lithium-ion batteries. So I think it's a promising technology.
Okay, thank you for that. And next questions regarding scale up. It is expected that when moving to industrial practice, the material and energy efficiency will be increased when compared to lab scale. How can you account for that in your LC modeling?
That was I didn't really talk in detail because of the limited time, but in the slides actually I showed that there was like several thermal equations that can be used to calculate to recalculate the energy required, the theoretical energy required for chemical reactions in the industrial level. So that is usually used when scaling up. but it's based on like small scale synthesis route, which means that the input material or reactants are the same as small scale or lab scale. We just recalculating the amount of reagents and solvents and energy required. And also like during the scaling up process, we also need to account for the solvent recycling as well.
Okay, thank you. Do you have any suggestion on how to conduct this upscaling for life cycle costing?
That is life cycle costing is I personally I have to say that I never did life cycle costing before, but I'm just sharing some of my thoughts. It's related to the amount of material required, right? Then it's also valid and also the amount of energy required. So we can use the same approach to calculate the amount of material and energy required, and then calculate, use like the cost to calculate the total cost, right?
Okay. Then next question. Currently in Europe, this is a move to avoid use critical raw materials. How this aspect can be integrated in your LZ models?
Yeah, that's a very good point that I didn't really mention that much about in the background system. That actually we can also consider like the recycling content of this critical material because of the regulation from the EU, and this can be considered in the background system. But then we have to make assumptions on like what is the recycling content, what is the recycling rate in the future years for different critical materials in the database, right?
Yeah, thank you for that. And thank you for all the questions submitted through the Q&A. Unfortunately, we can only address a few due to the time constraints. And it's wonderful to see such strong interest in this topic. And thank you, Shan Zhang, PhD candidate from Swedish University of Agricultural Science.
Thank you, Yulia, and also thanks to Swedish Life Cycle Center for inviting me. Glad to be here.
And if you're interested in exploring more about the environmental performance of emerging batteries, I recommend to checking out this select project and publications for further information. And all these links can be found in the event post on lifecyclecenter.se. And feel free to reach out Shan with any questions. Her email address is displayed here. And the life cycle talks are published by the Innovation Cluster for Life Cycle Perspective and Swedish Life Cycle Center. The next talk will be held on November 26 with Björn Spark from the Swedish Environmental Protection Agency, discussing how the life cycle perspective is being used in policymaking. To ensure you don't miss the next life cycle talk, follow us on LinkedIn and subscribe to our newsletters. Thanks for listening.